Our next speaker is a rising force in the machine learning community, blending deep research with hands-on innovation. Ms. Preethi Srinivasan holds an MS by Research from IIT Manipur, where her thesis focused on advanced medical image post-processing. She is the first author on papers published in ACCV, WIML and IEEE CBMS. At Sahaj, she has led the development of cutting-edge ML prototypes spanning video understanding, LLM fine-tuning and retrieval augmented generation systems. Her insightful blog series on LoRA and intrinsic dimension has not only deepened the community's knowledge but also earned her speaking spots at PyCon India 2024 and the 5th Elephant 2025. Today, Preethi will walk us through how techniques like quantized low-rank adaptation and PyTorch's fully sharded data parallel are making it possible to fine-tune massive models, even those with 70 billion parameters on consumer-grade hardware. With that, please join me in welcoming Preethi onto the stage.
Hi. Welcome everybody. Thank you so much for coming. So today we'll be talking about how to democratize LLM training / fine-tuning, because it's not, clearly it's not in everybody's pocket to be able to fine-tune / train. So communities like universities and labs everywhere have been making efforts to make this possible. So we'll try to see how can we get there in a few steps, as in we'll also look at the whole evolution of efficient fine-tuning, what people have been doing to make it efficient, and let's set an objective and let's see if we can reach the goal. Okay. So the objective here is to be able to make large language model training, large model training possible, right? Accessible, more so. So the question is, what kind of goal should we come up with to truly call this a democratic, to truly call training democratized, right? Cool. So the question we are trying to ask is, when do we call it truly democratic? And to answer that question, let's come up with a goal. And the goal would be the following. If we can fine-tune a 70 billion parameter model using only consumer-grade hardwares, like maybe, I'm not sure how many of you are familiar with 3090s and RTX 2080s and stuff. So if you can do a fine-tuning of something as large as 70 billion on such consumer hardwares, then you'll probably call it truly democratic, right? So this is a big challenge, because 70 billion parameter, even if it has to just like have the model in place, it's going to take you 140 GB, let alone making training possible, because there's a lot more memory required for you to train, because you'll have to store activation values, gradients, and a lot more, right? So, and this 2 bytes is also a very conservative estimate, right? Lot of models are today available in 32-bit format, or various kinds of formats. So this is the most conservative estimate. To just have the model in place, you need as much as 140 GB. So this is quite a challenge. Then evolution of techniques to make fine-tuning efficient have been going on in pretty much two parallel, or rather crisscrossing tracks. One track is to make the whole software architecture, as in the architecture of the model, the network architecture, efficient for fine-tuning. And the other direction people have been working on is on the hardware side. As to how do you, obviously you cannot have a GPU that will fit the entire trillions of parameter models today. So you'll have to figure out how to parallelize the whole thing. You'll have to figure out how to make training efficient while making it parallel, and inference and so on. So there's a challenge in the hardware architecture also. So there has been evolution on both directions. Today we'll try to cover up few milestones. There's been a lot of work in between the milestones as well. So we'll get till QLoRA, and we'll also see quickly around how things have been evolving in the hardware architecture. We will get till FSDP. And let's make the best of the two worlds meet. What if you can probably achieve your objective that we set out to in the beginning with by combining these both, FSDP and QLoRA. All right. So quick recap of what is fine-tuning. and what is the necessity of fine tuning. So in case of image data, suppose if you were to train your model on infinite amount of data, let's say about 20 million images, and you want your model to learn to classify the images between 20,000 categories broadly, which is animals, plants, etc. Right? So you have pre-trained your model to do the job. Now, suppose if your task at hand is to classify between these 1,000 varieties of fishes alone. Unlikely your pre-trained model will do a great job on this because it has not learned inert details about every fish possible. It will probably recognize it as a fish, but may not be as which kind of one of those 1,000 fishes. So this idea of adapting your pre-trained model or your base model for your downstreaming task, for your domain-specific task is called fine-tuning. This, the earlier example was image-based example. This is a language-based example. So most large language models, the LLMs that we call today, they have been pre-trained on infinite amount of data. You will want to fine-tune them on your personal domain-specific medical records or law records, whatever, like your engineering training modules, etc. So one question after listening to all of the talks earlier would be, why not just feed the entire document as a prompt, because Gemini can support about 2 million tokens or something, their sequence length. So so prompting is still not, it's not exhaustive. There will be a point when it will crash, right? Also, the previous speakers have discussed about how things can go wrong with just prompting, like needle in the haystack and so many other issues, right? So fine-tuning is really not off the chart. And suppose say this is your neural network. Again, I'm trying to abstract it away. There are too many details to things that we cannot cover in a 30-minute talk. So if this was your deep neural network, let's say your neural network has like 10 layers, and conventionally this is how people used to fine-tune. They used to keep the initial layers frozen, and they would only train the last layer for your domain-specific task. So this would learn how to classify between the 1,000 fishes. They would take advantage of the pre-trained model for the knowledge that it has learned on the infinite amount of data, right? So conventionally, people used to either train all the layers or a few layers, right? 1 or 2 layers. Now, if you were to do this for a large model in today's world, a Llama 3.18 billion, which is still not a large model, it's actually probably a medium or a small to medium model. It has about 8 billion parameters, 32 layers, and the last layer has about 218 million parameters. If you were to do conventional fine-tuning on a model of this size, it's going to be like very expensive, because the memory required itself to have it on the RAM itself would require you 8 into 10 power minus 8 billion into assuming 4 bytes per parameter, right? So, and you need additional resources to cache a lot of other aspects of training. So this is prohibitively expensive. So the idea that came up later is, how can you make it efficient? One of the main things that people were trying to answer is, how do you make it parameter efficient? How do you make it training possible so that I don't have to train all of the parameters, and it has to also fit in my memory? So the technique that came up was the adapter-based PEFT. Among many PEFTs, among many parameter efficient fine-tunings like prompt tuning and other things, adapter-based techniques stood out for a long time, right? So the idea of adapter-based PEFT is to add additional few extra parameters to your base model. You inject them into the base model. There is enough literature about how do you inject them, why should you inject them a certain way, etc. We'll briefly get into that maybe. So the idea is to inject these extra parameters and only fine-tune them and keep the base model frozen, right? And therefore, for your each downstreaming task, you might have to only save these extra parameters that you have injected into your base model. You don't have to bother to save the entire base model. So if you have 10 downstreaming tasks, you just have to save these small adapter green color pieces, these 3 of them, only those pieces have to be saved for each of your downstreaming tasks, right? So more about adapters. So one of the key properties of these adapters is that it has to be smaller in size compared to the base model layer. Otherwise, the whole point is lost, because we are coming from a point where it's all very expensive and too huge. So that's the first thing. Secondly, the initialization of those, again, by layer, I mean it's a matrix of numbers. Like most of y'all who are aware of deep learning network network architecture must be aware of the fact that when I say layer, I'm interchangeably using it to represent a matrix of numbers, right? Weights or numbers or whatever you call it. So those weights have to be initialized some way when you're injecting them into the base model. So that initialization has to be done right. If you don't do it right, then you can screw with the entire training process, right? So it can cause catastrophic forgetting. It can cause a lot of issues. Like it can cause very training will not be smooth. The convergence will not be smooth. It will be too zigzag, and that's not good for your learning process. So there's another fundamental question of how are fewer parameters even enough to fine-tune on your domain-specific data set? That's a story for another day. There's a blog series I'll connect you all to in the end of the talk. You can read more about it on intrinsic dimension and other things. Quickly, if you were to inject the adapters, one of the earliest ideas was to have the adapters in sequence. See, if these blue blocks are your base model layers, then these adapters are your injected layers. So the idea is to have them in sequence. So if you decide to adapt two of your base model layers, then you will keep them in sequence, one after the other. Now, two caveats of this process is that GPUs are meant for parallel processing. So you are effectively not using the GPU, you're not exploiting the GPU's capability because these adapters are small in size by design, and you're not using the rest of the space. And if it's in sequence, it's going to process them in sequence. So, and if it's in sequence, training and inference time is going to be longer, right? Because it has to go one after the other. So this paper called LoRA, which is published by Microsoft in about 21 or 22, they propose to have these adapters in parallel to the base model layers, right? So the other thing that they proposed is that having a base model layer is again, like adapter layer is again a layer of matrix, right? I mean, it's a matrix of numbers. It could be a full rank matrix, so they proposed instead of having a full rank matrix, break them into two low rank matrices, choose an R. So if your adapter matrix initially, if you chose to make it, let's say for example, 200 into 2000, carrying about 4 lakh parameters, you would break them into two small pieces, make it 200 cross 3 and 3 cross 2000. So effectively you're only carrying 6,600 parameters, but if you multiply them, you will get back the original dimension, right? So that's the USP of this paper. So quickly, if you were to look at the block diagram or the architecture of the algorithm, if these red blocks were your base model layers, these green blocks are your adapter layers because these are the only ones that are being trained. These are frozen, so nobody, that's why they're in red color. So your input copy of your input goes into your base model, copy of your input goes into your adapter layer, get multiplied. So two pieces of adapters, so call it LoRa A, LoRa B, gets multiplied. And once you multiply by design, you're going to get the same dimension back. If it's 20 cross 2000 and your adapters are designed this way, then the moment you multiply them, you're going to get the same size back. So you can do element-wise addition in the end of the output of the first layer, right? So that's the LoRa's USP. The other thing is that you can just plug this adapter away, save them in the hub. So, and when you want to fine-tune on a different fine-tuning task, if you want to use it for inference, get the base model from the hub, get your specific adapter from the hub, plug them back, use them for inference. That's their key takeaway. So if you were to implement this on a sample MLP of size, say, let's 1700 KB or something, your adapters will be as small as 51 KB if your rank is 2. So that's significant, and this difference will be really significant if you're using large models. So if you were to do the same thing with Llama 8 billion, and if you were to adapt only one layer with rank 2, then instead of having to fine-tune 218 million parameters, you would end up fine-tuning only 5 million parameters, which is like a huge win, right? So it's compute efficient, and amplification factor is a metric to understand how well your adapters have been trained for your downstreaming tasks. The paper, let's not get into the details of it, you can find them in the blog. The paper proposed or claimed that with rank as low as 2, even GPT-2 and GPT-3 were getting amplification factor, very, very high amplification factor, which means this is basically justifying the fact that you can use two low rank matrices and get away with the job, right? So Now, what's the limitation of this whole thing? Limitation is that for inference or for training for that matter, you need to have base model and the adapter on the RAM. You need to have, so effectively if I want to do 70 billion models fine tuning, I still have to have them somewhere, like my VRAM should be still large. So my compute is being optimized here, but my memory is still not a solved problem. So then came, if we were to solve for memory, the next idea is to quantize. So bits and bytes is the library which was contributed by University of Washington by Tim Detmers and his co-authors. It's integrated with Hugging Face. So what they proposed is that we will have this base, we will have this base model quantized. So instead of having them in 32-bit float or 16-bit float, have them in 2-bit integer, 4-bit integer, or whatever it is. So to be more specific, if this is a matrix with, let's say your base model was like 16-bit float or brain float, whichever format it is, what they'll do is they came up with this 16 numbers. They sampled it from normal distribution because their hypothesis was that all of these neural network weights, after having learnt on a specific task, will all fall into normal distribution. So they said between -1 to 1, I'll sample those 16 numbers and map any given number, any given weight to this one of these 16 values, right? And there will be a one-to-one mapping between this between each of these 16 numbers to integer numbers, 0, 1, 2, 3, 2, 0 to 14, 0 to 15, right? So end of the day, so instead of carrying this whole thing in the network, you'll only have to carry this, which is much smaller. That's the idea of quantization. But the problem is that you can only do inference with this model. You can't do training because training requires you to converge. Your loss has to converge over time. So if your loss surface is more like a slant plane, then there is, so what do you mean by convergence? So when you're changing the loss, you're asking how much do I change this weight so that in the end I can reduce the loss further, right? And that jump or that change has to be significant enough. If you are doing a step like the way we just quantized it, it's just 16 steps. If you were to do 16 steps, then the change has to be significant enough for you to fall further down. If your change is less, you can't fall. Whereas if your precision is very high, then you can fall much faster, right? So this, effectively your gradients won't change. They'll all be 0 all the time. It will not be significant. They won't be 0 all the time, but it's not going to be significant at all. So how do you make quantization work for training? So that's when this Tim Detmers and co-authors proposed QLoRA, which is you will have the base model parameter, base model weights quantized and have the LoRA weights in 32-bit format. So this paging optimization, which most of the operating system guys know about it. So there in software engineering, you page from probably secondary memory to CPU or, secondary memory to your primary memory or primary memory to your L1 cache and stuff. Here you do that, you pull, whenever you're doing a forward pass, that particular relevant layer, you will pull it from your secondary memory, dequantize it, use it, put it back in quantized form. So at any given point, you're having an overhead of quantizing and dequantizing because of the paging, but you're able to fine-tune a large model, which was never possible before. So these guys were the first ones to be able to fine-tune a 65 billion parameter model in as small as 48 GB VRAM device or a machine, right? So it's still not enough, right? It's still saying 48 GB, first of all, is very expensive. NVIDIA 48 GB is very expensive. It's about $10,000 or something. And also a 65 GB model will just be able to sit on a 48 GB GPU. You will not have enough space for saving other gradients, so you'll have to use a lot of other optimization techniques like gradient checkpointing, etc. You can check them later. So, and other thing is you can't use huge batch sizes, so your training is going to take forever. And even if let's say you compromise on that, even if your batch size is small, each sample sequence length should be limited. You can't have like a very long sequence length. You can't train on long sequences like Gemini is proposing, right? Because all of that requires memory. So there's your you're constrained on all of that. So it's like teaching an elephant to learn football in a very, very constrained environment. So let's now solve for time. This is where we get into the hardware architecture evolution. This is where they start meeting each other. So, again, data parallelism is again not a new thing for engineering folks. Distributed data parallelism is basically let's distribute the data. We are solving for time, right? So if I'm going to, in the earlier case, I'm going to use very small batch and the training is going to take forever. So what if I can parallelize the data? As in, I have a copy of the model on 3 GPUs. Let's say you have 3 GPUs, your yarn is supposed to say 3. And you have a copy of your model on GPU 1, 2, and 3, and you show them 3 different pieces of data, right? You're basically parallelizing the process of showing the data and training. So in the end of that forward pass and backward pass, you will have aggregated some gradients, right? So you just add them. So that's an overhead that you have to deal with. If you're doing, so if you have 4 GPUs, then your training is 4x faster, right? But now caveat is that each GPU should hold the entire copy of the model. No, that's not possible today, right? So this is another simpler diagram of the same thing. Say you have 3 layers which you want to train, L1, L2, and L3. And your GPU 1, you will have all 3 of them, L1, L2, L3. Your GPU 2 will have L1, L2, L3. GPU 3 will have L1, L2, L3. But you're showing them 3 different pieces of data, D1, D2, D3. That's the separate, unique, separate ones, right? So this GPU 1 will process data 1, GPU 2 will process data 2, and GPU 3 will process data 3. In the end of forward and backward pass, you will do gradient accumulation, right? You will do this. You will corresponding gradients you will have to add and come up with one number and give a copy, send a copy to all the GPUs. So your second round will start with these gradients. Okay, that makes sense, right? So yeah, so this way your training can be faster, but the caveat is your entire model, model may not fit into a GPU. Maybe if your model is 2 billion parameters, it can fit, you can have multiple GPUs and make the training process parallel, but this is not going to work for very large models. So this process of accumulating gradients and sending a copy of the sum of the gradients or average gradients or however you want to reduce them, the process is called all reduce. Okay, there's this library called NCCL, which is normally called NCCL, NVIDIA Collective Collections Library. These guys, this library basically works on foundational data movement on GPU. They have the code to do all of those movement. So there's all reduce, there's all gather, reduce, scatter. These are some of the popular operations used by all of these parallelizing algorithms, which they have implemented, right? So you can't. This is one of the famous, not most used library. There's one more, Igloo or something, but this is the most used library. It's called NCCL. Yeah. So what we saw, the operation that we saw there is all reduce. Okay. So then let's solve for the memory again. We just discussed that your models are going to be way larger than what your GPU can support. So then comes the model parallelism. So if you want to solve for memory, you can split your model into pieces, put them in multiple GPUs. So have that one data, D1, that will see GPU 1 at any given point of time. At the next instance of time unit T1, time unit T2, D2 will be the data 1 will be seen by your L2 layer, right? And these white color things are idle, right? Your compute is basically idle. These are called bubbles. So you're using on compute. These are all idle time. So a single consumer, first of all, can't hold 70 billion. So you're going to split them. And the caveat of doing model parallelism is that you're going to waste on compute. At any given point, suppose you have 8 GPUs, you will waste on 7/8 of the GPU because only one of them is functional. Then, so this is another fancy diagram taken from here. So if you have 2 pieces of network, like we saw earlier, the first layer is going to be seen at any given point by only 1 GPU, and then the intermediate results, the activation values that comes out of this layer, the first layer, will go into GPU 2, right? Now, this is just to show that there's a lot of idle time because you will have to accumulate gradients after the entire forward and backward pass is done. So you're wasting time on that as well. So there's a lot of idle time. Now let's solve for memory and time. Okay, so the popular idea is pipeline. Pretty much every area of engineering uses it, including mechanical engineering, etc. Anybody you can think of. That is, you divide the data into micro batches. So at any given point, this is basically to optimize on the idle time. So your micro batch 1 is going to look at L1. By the time micro batch first micro batch goes to L2, you will start sending the next micro batch to L1. Right? You're basically parallelizing this process. So after the first 3 steps, your GPUs are never going to be idle. They're all going to be functional all the time. They're doing some work. The problem with this is there's a lot of communication overhead because you have to move the data across GPUs and you have to move the gradients across GPUs. Here, the most naivest way of doing this is you will wait until the whole process is over for both forward and backward, and then do gradient accumulation. Now nobody wants to waste that time either. So what people end up doing is, while backward propagation of one of the layers is happening, they'll want to do forward of something else, which is again tricky, because you will have to sync the gradients really well to be able to do that. So there's a huge overload of pipeline model parallelism. There's this library called DeepSeed by Microsoft. There are algorithms called Zero, etc. if people are familiar with it. So they came up with data and model pipeline parallelism. So they said, model also will parallelize, data also will parallelize. I was not able to make a simple diagram for this because that became too complex, so it's just their paper's diagram. Again, with lack of time, so you can go and check out the details, but one of the caveats that I want to discuss is that it's major communication overhead. Now the next thing that we want to do is, let's solve for time, memory, and communication. That's when FSDP came up. Right? It's fully sharded data parallel. They had multiple goals. They had to save on memory, they had to save on time, they had to save on communication overhead. As in, they want to do as less communication as possible. So they proposed the following. You have 3 layers, L1, L2, L3. Each layer you divide into 3 pieces, A, B, C. So your GPU 1 will have L1A, the first part of the layer 1, first part of layer 2, first part of layer 3. GPU 2 will contain second part of layer 1, that is L1B, L2B, L3B. And your GPU 3 will contain the third part of all your layers. So at any given point of time, there's this process called reduce scatter. So what they realized is, the all reduce that we saw in DDP, their goal was to achieve as good an accuracy as DDP while parallelizing the model, right? So they realized that the operation all reduce can be divided into 2 parts, which is reduce scatter and all gather. And that's what they're trying to implement here. So they said, let's reduce the scatter at any given point of time. Each GPU, these are the host pieces, which will never move from the GPU. They're always there. At any given point of time, they borrow the remaining pieces from the other GPUs. Okay? So at T1, GPU 1 will borrow the B and C parts from the neighboring GPUs. GPU 2 will borrow the A and C parts from the neighboring GPUs. GPU 3 will borrow the A and B parts from the neighboring GPUs. Now, all 3 pieces of data will do forward pass on layer 1. Is it making sense? I can repeat it if. So the data is also being parallel, the model is also sharded, and the communication here is that you will borrow your rest of whatever pieces you don't have. The host has only 1 piece of the layer. The rest of the other pieces will be borrowed. And you will do the same operation which you did earlier with DDP. You will aggregate them, you will reduce them, whatever. And then you will make a copy and keep it in all the GPUs. That communication has to happen. And then you will flush the pieces that you borrowed. You'll only keep the host pieces, host parts, or host part of your layer. So you're always borrowing, using, flushing away. Borrowing, using, flushing away. Another thing they can do is, while doing computation, you can also communicate. So because they both are independent activities. Unlike the earlier DeepSeed Zero guys, they were able to make this activity independent so that communication never interfered with computation, and they also got edge on the time. So that's how this algorithm became very famous. This is by Meta. They came up with this in 2022. So This is the diagram from their website. Now, let's go back to the objective that we started with. We started off saying there is software architecture evolution and hardware architecture evolution. So we saw, we ended here at QLoRA, we ended here with FSDP. If you now mix both of them, if you merge FSDP and QLoRA, that is you manage, I don't have a diagram for this, if you manage to host the pieces of your layer which are not trainable, but only move the ones that are trainable, the quantized ones will sit in the host, and the unquantized ones which are being used for the forward pass will keep moving through the GPUs. FSDP and QLoRA is possible, and you can actually achieve this goal where you can train a 70 billion model on a consumer grade hardware. But yeah, there are a lot of challenges if you want to get into details as to you can only move the model into a GPU and then quantize them. You can't. So if you get into details, you will have a lot of hiccups. You can keep solving one after the other. We can get into detail on a different talk just for FSDP next time. So there are other things that people do to make efficient training. They do CPU offloading, which is also done in most engineering, like that paging. When you don't want the parameters, when you're not using them, have them offloaded in the CPU. Use them only when you want. So CPU offloading is again used with FSDP. Then gradient checkpointing is where you don't, again, gradients require space to store somewhere, right? So you don't store gradients everywhere, in every layer. You store gradients only at some sync points, and when you're doing backward pass, when you want the gradient information, you do a forward pass at that point again for those few layers, right? So that's called gradient checkpointing. There's activation checkpointing. There's flash attention 2 paper which made a lot more optimization on how training can happen. I'm not aware of those details. While we are speaking all of this, the world is also doing a lot of work on the reinforcement paradigm. People are discovering better and better policies for making training more efficient. DeepSeek is one of the popular examples. So yeah, that's it. Thank you. This doesn't have any of the resources. I'll try to make a resource and send it across to all of you. Maybe a blog or something. Thanks.
So how does Unslop and even Apple's MLX
Right. MLX is a machine learning platform. It's like PyTorch. Okay. FSDP is implemented in MLX.
Okay. So how does Unsloth compare to these?
Unsloth, flash attention is Unsloth's work. So so they did kernel level. They changed a lot of work. They did a lot of matrix multiplications. They optimized a lot of them, and yeah, Unsloth also used the other things and made training a lot more faster.
Okay. So actually, when we talk about consumer hardware level fine tuning, so Unsloth comes up as first probably, I guess.
Unsloth, at least whatever is open source, is all single GPU stuff. They haven't made any of the multiple GPU services open yet. Okay, so maybe that will come later, but I'm yet to see if we don't know what they are up to.
Thank you.
Yeah. Cool. Thank you so much.